Welcome back there, everybody. So, if you are watching this on schedule, it is Friday, April 3rd. So, happy Friday. Just like a few other videos, we have a lovely special guest with us today, Miss Vampus.
Hi everyone, happy Friday. Hope everyone's having a lovely week so far and that you're enjoying your Friday. All right, so before we go ahead and introduce our topic of entropy, there are just a few dates that we want to highlight. Okay, you do have homework that's due today, so make sure that you submit that.
So, the castle learning that says PE diagram and entropy, that is due by 11:59. Again, if you have issues, let me or your actual chem teacher know. But by this point, we should be on a roll with that.
Mm-hmm.
So, moving forward, you have, it doesn't print on paper, but a GIF of a dog sliding down a hill. So the question is, what's spontaneous and what is non-spontaneous? So let's hold off on that a second and go through the definitions of what spontaneous and non-spontaneous actually mean, and then we can apply it back to this lovely GIF.
Right, so as we said, there are two types of reactions. And when we're talking about reactions, just to, like, in case you don't know what we're talking about chemical reactions. And so with any chemical reaction, we have reactants and something happens, and then we have products, okay? So the two types of reactions that can occur are either spontaneous or non-spontaneous. So looking at your slide, number 3, a spontaneous reaction is one that is able to proceed without needing an outside source of energy. It is considered an exothermic reaction. In other words, heat is released. Now, with a non-spontaneous reaction, this type of reaction needs an input of energy. Endothermic reaction, heat is absorbed.
So when we're looking at this, if we're looking at an endothermic reaction, we're saying it's non-spontaneous because that reaction will not happen unless you give it that extra push of energy. And so that push of energy is that heat that needs to be absorbed. And again, when we see it in an equation, it's written as a reactant. On the other hand, a spontaneous reaction happens on its own. It does not need that extra push, so once it's going, it's going. And those are exothermic reactions when the heat is released. So,
right. And if that was written in the chemical equation, it would be on the product side.
exactly.
Okay.
So if we go back to the dog GIF example, the dog's now currently sliding down. So if a dog is sliding down, it's not, as soon as it's going. And going downhill would be the spontaneous part. But now that it's dragging its sled back up on its own, that doesn't happen on its own. The dog needs to put energy in to drag that sled all the way up. So going up would be non-spontaneous. Going down would be spontaneous.
That's right. Okay.
Okay.
Good.
So a spontaneous reaction happens when, one, less energy, so lower enthalpy. Remember, enthalpy is that delta H value that we talked about. And we wrote it with a giant H because that essentially just meant heat. And so exothermic reactions are favored because the products have less energy. On that PE diagram, you're ending a lot lower. Another thing is favored when you have great randomness or disorder. So randomness and disorder is essentially what this video is focusing on, and that gets a fancy sciencey name that we'll talk about on the next slide.
Right, so moving ahead, look at slide number 5, entropy. It is the measure of disorder or randomness in a system. So in nature, greater entropy is favored. And so what that means is that randomness or high amount of randomness and high amount of disorder is actually favored. And if you look at the diagram, okay, substance A compared to substance B, which one of these two have higher or greater entropy? That would be substance B. Okay, it's like highly random and very disordered. As opposed to substance A, everything is aligned, everything is situated and in place.
Okay, so again, like Ms. Sanchez had said, substance A represents something with less entropy because it's very highly organized. If something has high entropy, it's very, very random. So just like with enthalpy, or I can't, you know what I mean. Just with enthalpy, we made that H big. With entropy, we make that R big because that's talking about randomness. So entropy is a measure of randomness, organized. Okay. So
can we just go back again? So basically with enthalpy, right, it is concentrating on the heat, yes?
Yes.
And then with entropy, it is concentrating on randomness. That's what its focus is about.
Yes. Okay. So moving forward, we have diagrams of a solid, a liquid, and a gas. So if you look at a solid, it's highly organized, and that's one of its characteristics of how these particles are arranged. So if you're highly organized, you have low entropy.
Right.
Oppositely speaking, we have gases. They are highly unorganized or disordered, and that means you have high entropy. So as you're moving from a solid to a liquid to a gas, you get more and more random, you get more and more unorganized, you have more and more, a higher and higher entropy.
Right, and this is the slide that we really want to focus on, because on Regents questions, most likely they will ask you about the state of the substance, okay, or the phase of matter, and as it changes from like solid to gas or solid to liquid, which one has a higher entropy or less entropy. So this diagram is your go-to diagram to do those questions and to remember, the level of entropy. Okay?
Okay.
So moving forward, okay, we're going to go to this picture. Which picture has more entropy? So on the picture on the right shows a pretty organized, well, let's take a look. That's a plant, right? And it is in some sort of planter. And then on the left, we have a toddler, and it has this plant laid all over the room. So which one of these depicts a higher entropy?
I would have to say A. If it has more entropy, it is more unorganized. And if you look at the pot that's spread all over the floor, that's not organized. That is very, very messy. That is literally the definition of entropy.
Right. So it's highly disordered. Okay?
So if we look at the examples with the rooms, the room on the left, so we're going to write that as A, is a very clean basement living room type place. And B looks like everyone's going through a spring cleaning phase.
Yes.
So, which one do you think would have more entropy? The clean room or the spring cleaning room?
Oh my, do you notice that there's a man on the bed?
Oh my god. There's that man.
Oh my. Okay. Well, if I were to I would say that room B has higher entropy compared to room A. Okay, this one is highly disorganized, highly random, and it is a complete mess.
That would be absolutely correct. Great observational skills with that man in the corner.
That looks really exciting. All right, moving ahead.
Okay, so let's kind of bring chemistry back into this, because we've been talking about plants and weird men. So it does relate to chemistry. So when entropy increases, again, that randomness, writing and speaking is very hard at the same time, increases when you have more stuff in a reaction. So for example, if you have a solid block of NaCl, that's one molecule of stuff, throw that into some water, and you get both of the ions. Now you have more pieces moving around. So if you have more stuff, that automatically makes stuff more unorganized.
Okay.
Another thing to point out is that your reactant is a solid and your products are AQ. Remember, AQ stands for aqueous, which is something dissolved in a liquid. So going from a solid to a liquid, that also is a key to tell you that entropy or randomness is increasing.
Right. So, guys, just to, in case you don't know what we're talking about, right now we're talking about factors that make entropy higher, okay, or like increases entropy. So the first thing we just talked about is the phase of matter. Okay, solids generally have a lower entropy compared to liquids. All right, so the second factor is an increase in temperature. So when there's an increase in temperature, entropy increases.
Remember, temperature is the same thing as average kinetic energy. So if you have a higher temperature, you have a higher average kinetic energy, which means you're moving a lot faster. If you have a whole bunch of people just kind of walking, that's somewhat organized. But if you picture everybody running, that just leads to way more chaos and more disorder.
Right. So moving along to the next factor, when a gas is formed from a liquid or a solid. So again, there's a phase change. Gases generally have higher entropy compared to either a liquid or a solid. And then lastly, when a liquid is formed from a solid. Again, solids have lowest entropy compared to the other states.
Remember, that's that slide we talked about a few slides ago, that as you progress from a solid to a liquid, your entropy increases.
Right.
Okay. So, moving on. Here is a lovely meme because we know you've missed these.
Of course.
So, you have this kid and, I guess his parent, that he's in 4 different scenarios and they look kind of messy. And the parent's like, yo, how did this happen? And the kid goes, entropy. So, one of the things we like to mention is that, yes, the universe likes to favor entropy. So what we like to say, the universe is a stereotypical teenager, meaning it has low energy, it's very lazy, and is highly unorganized. So that is what the universe enjoys and likes more, and that's what it favors. But if somebody at home says, oh my god, your room is a mess, clean it up, you can't just say, this is what the universe wants, I'm giving it what it wants. No, clean it up. But the bottom line of the picture says, this is why we don't teach our children about entropy until much later. So we think you're old enough and wise enough to handle this information.
Yes, absolutely. And of course, when we're talking about a stereotypical teenager, a lazy, unmotivated, disorganized teenager, we're not referring to you, obviously.
No, you guys are not like that.
No, absolutely not. All right, guys. So that wraps it up for the PowerPoint, the information. So now let's go ahead and practice some Regents questions. Okay, so the first question we have in front of us is, given the balanced equation representing, my thing cut off, what is it?
A phase change.
Oh yes, here we go. A phase change. Okay, so take a look at this chemical reaction, all right? And we have on the on the reactant side, we have a solid. So everyone go ahead and circle that solid, that S, okay? And then for the product side, we have a gas. So circle the G. We want to find out which statement describes this change. So they want to know if this is an endothermic or exothermic reaction, and whether or not entropy increases or entropy decreases. So let's talk about the phase change, right? From a solid to a gas. what do we know? Does the entropy increase or decrease?
We know that going to a gas, that entropy is going to increase. So we can get rid of A and C.
That's right.
The next thing you want to look at is energy and where it's placed in the reaction. So now we know it is a reactant, which means it is absorbed, which means it's spontaneous. But it is also an endothermic reaction, so that makes it answer choice B.
Right, so there are like a couple of components that go into this question. So if you're sitting here like, what just happened? What did you guys just say? Just take a moment and pause the video and just go ahead, read the question over, and think about what does endothermic mean, what does exothermic mean, and just try to redo this question on your own to make sense of it. Okay?
Okay, moving forward with number 2. Number 2 says the entropy of a sample of water increases as the sample changes from. So we talked about going from a solid to a liquid to a gas, you're increasing that entropy. So if we're going from a gas to a liquid, your randomness is decreasing. If you're going from a gas to a solid, again, you're getting more organized, that entropy decreases. If we jump down to choice D, liquid to a solid, again, you're getting more and more organized, so your entropy is decreasing. But if we look at C, liquid to a gas, you get more and more unorganized, and that is why C is your answer.
That's right.
Okay. Moving forward with number 3. Which 1 mole sample has the least entropy? So that means you want the most organized answer.
Right. And if you take a look at all of the choices, well, first of all, you guys should have underlined least. Okay, we always want to practice good annotation skills when we're doing these questions. So you guys should have that underlined or highlighted, least entropy. And when we are thinking about least entropy or lower entropy, right? The things that should come to mind are like the phases of matter. Okay, it should be solid, right? What kind of temperature? Is it a low temperature or a high temperature? It should be low temperature. So looking at your options here, okay, we want solids. That's it. We want solids and low temperature. So that leaves us with choice A, since Br2 is a solid, and all the other ones are either liquids or gases.
And that's it. So just as we're annotating the questions, that's how you should be approaching these questions as well. Okay. Number 4 says, a thermometer is in a beaker of water. Which statement best explains why the thermometer reading initially increases when lithium bromide is dissolved in the water? So, there's a lot to unpack in this question, but we're talking about how the thermometer is increasing. So that means the temperature has to increase. So if we're talking about your reactants and your products, if the temperature increases at the end, that means heat has to be a product. So if heat is a product, if we change colors here, that means this has to be exothermic. So if it's exothermic, we can get rid of all of the answer choices. So it has to be D. But if we take a closer look at, so answer choice C is absolutely wrong. But if we take a closer look at A and B, we're talking about a solid being dissolved into water. So remember, aqueous means liquid. So a liquid in a liquid, entropy isn't really changing within that. If we look at choice B, again, liquid and liquid, the entropy is essentially the same thing. So that's why A and B don't make any sense. This one was a pretty tricky one though, but this is kind of as hard as it gets in terms of entropy-based questions.
So this question would be a good one for you guys to just unpack, sit down down for a second and just like really dissect what this question is asking and all the components that go with it. And when you have like a good grasp of this kind of question, that pretty much means that you're pretty solid with this concept.
Okay.
All right, go ahead.
Let's jump into number 5. Number 5 is a pretty easy one to end with this portion. It says, in terms of energy and entropy, systems in nature tend to undergo changes that would. Remember, we're thinking that the universe is a lazy teenager. So a lazy teen is messy and lazy. So low energy and high randomness, which is high entropy. So that is what C is. The universe is like a lazy teen, not that any of you are, but that is what entropy bases itself off of.
Good. All right, so now we're going to go ahead and do some more entropy practice. So look down towards the chart, okay, that is provided for you. And we're going to take a look at the reactions. We're going to examine the change in entropy, whether or not it is increasing, decreasing, or whether there is even a change. And you're going to look at the reasoning. Now we're going to just going to tell you the answer, change in entropy. The key is posted up for you on our website. So if you want to go ahead and check the reasoning part, you can click on the answer key. All right, take a look at the first one. Silver, chlorine, silver. Okay, so with this kind of reaction, we're going to take a look at the phases. Okay, with the reactant side, we have aqueous and aqueous. The reaction happens, and we then end up with a solid. So going from an aqueous solution to a solid, what is the change in entropy? Is it an increase or decrease?
I would say decrease, because things are getting more organized as a solid.
That's right. So the reasoning is that the solid is formed.
Okay.
Right?
The next one, we can look at the phases of matter. We're starting with a liquid and we're ending with two gases. So if we're going from a liquid to a gas, we're getting more and more unorganized, which means entropy
is
increasing.
Right? The reason is because gas is formed.
Okay. Number 3, if we look at phases like we have done for the last two, we see that we have all gases. Well, that's not going to help us now. So we have to look at, let's look at how much stuff we have on each side. So on the left-hand side, you have 1 mole of CO2. So remember, you have that invisible 1. And you have 3 H2s. So that means you have 4 moles of stuff on the left side.
Mm-hmm.
On the right side, each of those have invisible 1s. So you have 2 moles or particles on the other side. So if you're going from more stuff to less stuff, are you more organized or less organized? If we're going from more stuff to less stuff, you're getting more organized. So if you're more organized, that means you have lower entropy. So it does take a second to kind of wrap your head around it. Okay. Moving forward, we're almost done here. You can tell we're having a blast doing this with you guys. If we look at, drop my pen, solids as a reactant, and we're ending with solids and gases, again, that entropy, that randomness is going to increase. Okay.
And the reason is because gas is formed, and also another thing that we didn't mention is that there's more stuff as well, if you're going to look at the number of moles.
The next one, everything is a gas, so that's not going to help us. So if we look at the amount of stuff on either side, we have 2 moles of stuff of reactants. We have 2 moles of our products. So that doesn't help us. So this is not a trick question. You don't need to overthink it. There's no change. That's it. Entropy isn't changing in this example. That's 100% acceptable. It is okay.
Nice.
Okay. 3 more, then we're done. Next, we have a solid, and we're ending with a solid and a gas. At this point, this should be kind of second nature. As we're becoming a gas, you're more unorganized, so entropy increases. The second to last one, you have gases and gases, and then you're ending with aqueous and liquids. So you're getting more organized, so entropy decreases. And lastly, a liquid to a solid means you are going to
decrease, okay, because the phase change is liquid to solid, and we all know that solids have the least amount of entropy. All right, guys? So we hope you enjoyed this session together. And if you do have any questions, just pause and rewind and re-listen to whatever section you need more assistance with.
Again, we enjoy that you're listening to our educational chemistry podcast. We hope you come back tomorrow for more information. On that note, have a wonderful day.
You too.
Bye.
Bye.